if you saw the previous video, you can tell I'm just jumping straight into the next part, part C for homework 2, separations. So now we're going to explain and implement code for calculating the bubble pressure, dew pressure, bubble temperature, and dew temperature for a 2-component system this time, not 3. So our 2 components are going to be isopropanol and water, and rather than how we calculated the bubble and dew pressure and temperatures in the past, this time we are using the NRTL activity coefficient model, so it might look a little bit different than what it looked like before. And then we want to generate the constant temperature VLE graph at 350 Kelvin, and then we want to also make a graph at 1 bar, so that's going to be isothermic graph, and then our constant pressure is going to be our isobaric graph. And then we are also going to compare the plot with figures online. That's just a good way to double check and see if our calculations and graphing was right. And finding an isopropanol water system should not be too difficult, because that is pretty typical components to have. And I'm just going to jump right into the code now. This time I'm just going to build on the code that I had previously from part B, and I'm just going to start a new section for part C, and I'm indicating that so I don't get confused, although I might get confused anyway. So we want to set our properties, and since I used P above, I want to use something different, so I'm going to do PR for props. And we are doing isopropanol and water, so I'm just going to delete this toluene. Oops. Yeah, okay. And as I said, we're starting off with these calculations first. And before our isopropanol was 30, our water was 30, and our toluene was 40. This time, I'm going to, I think, keep the isopropanol as 0.3 and just set the water as 0.7. But obviously you can change that. Start with our bubble pressure here, because that one's pretty simple. So define bubble pressure, and then I want to specify that this is using the non-random to liquid model, using a given x and t. From Raoult's law, we know that yp should be equal to x times the property NRTL PR.NRTL gamma at the composition and temperature given times the vapor pressure at that given temperature. Pressure is the sum of the partial pressures. We want to return the pressure, and that's the system pressure, and yp divided by p. Next we would like to do, let's do the dew pressure, and then we'll get into the temperatures after that. So again, we're going to define dew pressure underscore NRTL to indicate that this is NRTL. The rest of what it gave me is not accurate, so I'm gonna need a Y given. So for bubble, we need the liquid composition. For dew, we need the vapor composition. T, our number of iterations is going to be, let's do 100, and we can do a lower tolerance because we want high accuracy. We want to say the vapor pressure is equal to PR.P VAP at that temperature. And then an initial guess is we're going to create ones like y. Now we want a for loop for I in range n iterations, so we're using this guy up here. I need to add parentheses. I'm just going to call this P0. It's the calculated pressure from Raoult's law. So we're going to have 1 divided by the sum of y divided by the gamma guess times the vapor pressure. X is going to be y times P0 from above divided by the gamma guess times the vapor pressure. And then here we're quickly going to normalize this so that the sum is equal to 1. I guess instead of calling this G guess, I'm just going to call this gamma. And I'm just going to comment out that this one is a guess. And then below here, we're going to update the gamma value with the newly calculated one. And then P1, P0 is just the older temperature and P1 is the newer temperature. That's 1 divided by the sum of y divided by gamma multiplied by the vapor pressure once again. And then if the absolute value of P1 minus P0 divided by the P1, if that's less than our tolerance, which I defined up here, it's going to break the simulation. And then once that for loop is done, so I want this to be under the definition of dew pressure, but I don't want it to be inside the for loop. We're doing the final calculation of X using the new pressure, dividing it by the most recently calculated gamma times the vapor pressure, and then we need to normalize it again, and we're going to return the new pressure. We're going to return the new pressure, X and I. And basically we needed this for loop because X and gamma both relate to each other. So we kind of go through this until this is true, and then our for loop breaks unless we reach the end of the iterations. Move forward with the temperatures. So we're going to start with the bubble temperature, and then we'll do the dew temperature. I'm going to keep these titles kind of similar to each other, so I'm going to call this bubble T underscore NRTL. Again, bubble, we require the X, so the liquid composition. This time the pressure. We're going to set an initial guess by summing up basically the weighted average of the pure component boiling points of isopropanol and water, which again, same with everything else, is getting pulled from that file, from that import, I should say. So that's X times PR dot boiling point. And then within here, I'm going to call this EQN, so it's just an equation. So we have NP dot numpy dot sum. We're doing X times PR dot NRTL gamma, X and T arguments. We need to multiply this by the vapor pressure at that given temperature divided by the system pressure, all minus 1. And then we want to find the root that makes this equation 0. So we want to optimize root scalar the equation above. x0 equals t0, the secant method. Then we'll return the temperature and x times the property NRTL gamma x t times the vapor pressure divided by the system pressure. Then just to see what this looks like, I'm going to run these really quick. So give me a split segundo. I'm gonna call this x instead, and t equals, I'll just use 350 since that's something that we're doing. And as you can see, it gives us the x, the liquid composition for each of our components, isopropanol and water. I just wanted to do this before I get into the due temperature because that that function is probably the more difficult one out of these. So let's do, I'm just going to change this to y and run this. So that runs correctly, or I hope it's correct. And we just did this one, our bubble temperature. Going to see how that works out. Just use our usual pressure of 1 bar. It would be helpful if I could type secant and not secand. Okay, there we go. So running this, we know that it returns the temperature as well as this right here, which is our compositions. And so I'm just going to delete this since that was just to make sure that all of those functions were working properly. And now we can do the due temperature. So I'm just copying and pasting this from our previous homework where we used a gamma equal to 1, also known as this was an ideal simulation. So we are assuming that the components all interacted ideally with each other. And we can't really use these now because of our activity coefficients, and that's why we had to recalculate these. But this is going to help us calculate, these are going to help us calculate our due temperature. So again, with due, we need to give the vapor fraction and the pressure. So I'm going to call this the due T underscore NRTL YP. And the reason for having these due P and due T functions above was to have some good starting guesses without having to type out all of the equations again. So if this were ideal, this would be correct, but it's not, so we're just going with that as our starting guess, and then we'll see how the interactions of the system change this. And then we're going to combine the vector of T0 and X0. I'm going to define another equation, V. This is like what we did for the bubble temperature. So we're going to solve for the root of this. T is equal to the, that index, X is, and remember we combined the array, and we have that there. And we would like to return numpy.rpr x times pr dot NRTL gamma, the given x composition and temperature, pr dot the vapor pressure at that given temperature, divided by p, subtract y, and pi dot sum x minus 1. And then outside of this function, but within this do temperature function, we want to solve for the root. So optimize root of our equation at V0. And we want to return these values right here. I also forgot where I copied this from. I needed to change this to PR because that is what I called my properties. I'm just trying to see if I can run this as is. And I think I did it again somewhere. Yeah, okay, it was within what I copied. So that's why you have to be careful when you do that. That probably wasn't a good idea on my part, but R underscore is used to concatenate, and I added a P to all of those, so let me try to find them, because they need to be changed, because that is not correct. I have no idea why I would do that. Yay! So this is what it's returning, and we're not quite there yet. I'll just leave that down there. So now we're doing do T NRTL2. We need to transform this so that the x is always positive. And then temperature in there. Make sure I just keep that as R. I'm going to define our equation again. Temperature is equal to V0, so just like we did above. And then we want to basically reverse the transformation that we did to get back to x. So numpy exponent V, like so. We need to divide by the sum of the exponent, these indices, plus 1. And then getting back to x, we have x is equal to xn1 from above, 1 minus the sum of xn1. So xn1 is going to be our liquid composition of the, I believe, the isopropanol, and then then this right here, 1 minus the sum, that's going to give us the liquid composition of the water. Then we'll return x times gamma xt multiplied by the vapor pressure at that given temperature divided by P minus Y. We're going to optimize the root of this function using TV0.x. I don't need to return anything there. Yeah, so we have we're optimizing the root of this equation. Then we want to reconstruct our final x fractions again. I think I can take these, just take those and make sure that my tabs are correct. And I was trying to run this, but I completely forgot to put what I want to return. So I didn't have a return underneath this function, so it couldn't return anything back to me. What I want it to return is this V0 and x. I need to update it. Okay. Let's see if I can compare the two. Okay, so that's just two ways to do it. Basically, I wanted to show both of these because it's what we ran through in class, and for me at least, this is a lot easier to understand than this, but to each their own. So looks like my dew temperature, bubble temperature, dew pressure, and bubble pressure, I was able to test them and they all worked out. So our next step is to generate the constant temperature binary VLE of isopropanol and water at 350 degrees Kelvin, our isothermal graph. So this is going to be our VLE graph, isothermal at 350 Kelvin. So our first thing is to set the temperature to 350, and our x1s for the graph, lens space, 0, 1, and 101, so that we get those 100 divisions. We're going to create an empty y1s array because we do not have those yet, as well as a bubble P array. I'll just call it that. So now what we want to do is we want to do a for loop so that we can basically loop through all of the x's, the liquid compositions, and then calculate the corresponding equilibrium pressure, and that's how we're going to graph. So for x1 in x1s, which I set the x1s up here, oops, y1, and I don't really care about this value, I'm just using an underscore, that's like a placeholder value, and I'm doing bubble P NRTL, and an array of x1, x2, which is 1 minus x1, and t. Then what we want to do is add bubble P to the bubble P array. We want to add the P that we calculated, and we also want to add the y1. And then after that for loop, I just want to make sure the bubble P array is updated. So we have numpy.array and bubble P array. Y1s, again, we're making sure that's updated. Going to make subplots like we usually do. We want to add scatter, where the X is the X1s, Y is the bubble pressure array, and this name is the bubble. This is the this is the bubble curve of our graph. And remember that in this type of graph, the bubble curve is going to be at the top. And then we can take this guy here, paste it. Instead, the X's are going to be the vapor compositions, this array. The rest should be the same, except this is the dew curve. Then I would like to update the layout like I typically do. Then I want the figure to show. Make subplots, not make subplot. This should be figure equals make subplots, because that is what I'm calling the figure. Hopefully I found all my errors. Okay, let me make this less tall. I don't know why I made that so tall. As you can see, right here we have an azeotrope where they're touching. So separation there would be, depending on how you do it, would be very difficult. And the last part, we want to create a constant pressure VLE graph at 1 bar. So this is our isobaric VLE graph. And then we'll also want to compare the two figures with plots online. I forgot to mention, I'm going to do a TXY diagram, which is the constant pressure, and I'm also going to do an XY diagram. This is our VLE graph. Isobaric at, my memory's so bad, I think it was at 1 bar. Yeah. So we'll want to set the pressure equal to this, which we know that this is 1 times 10 to the 5th because we're converting between units, but this is 1 bar. I'm gonna steal from what I have above, and instead of a bubble P array, we want a bubble T array. And honestly, I'm gonna, because I can and because I want to, I'm going to copy and paste that and then just change some of the values. So for X1 and X1s, we're doing temperature, not pressure. We're doing the bubble temperature, NRTL, and we're supplying the pressure with this pressure above. And then we want to append to the bubble T array, and again the Y1s. Again, changing this to, it works the same way, I'm just changing the source, and I need to make sure that I change everything because otherwise it will come out wrong. That's the negative side to like copying and pasting and changing code. This time I'm actually going to do a 1 row but 2 column. I want to have both of the plots next to each other, the TXY and the XY equilibrium graph. And then we can add titles. The TXY diagram at 1 bar, as well as the XY diagram at 1 bar. We're going to add a scatter, x equals x1s, y is equal to bubble T array. The rest is the same, except I need to specify that this is row 1 and column 1. Similar thing here, change bubble P to bubble T. This is the do curve, and I also need to specify that it's in that first graph. So this is the TXY diagram. And then XY diagram below. Add scatter, x equals x1s again, y is y1s this time because it's the x and y graph. This is supposed to be, there's supposed to be a parentheses there. Row is still 1, but the column is 2 because we're starting a different graph. We don't want it to interfere with the TXY diagram. And then show legend is equal to false. And then we want a 45-degree line. So we're going to add one more scatter. X is equal to 0, 1. And y is equal to, 0, 1. Same row and column as above. We can do lines, line, color. We can do gray. Show legend is equal to false. And then we're going to update the layout just with a width and a height and see if I have any errors, because I typically have at least one typing error. Okay. Okay, I fixed it and it was all due to one small error. Let me see if I can quickly find it. So in my bubble temperature, I knew it was probably in the bubble temperature because down here we were using the bubble T NRTL, and I had set this as a root. I tried to return T instead of returning the root. So I fixed that, and sorry, my laptop is just being super slow. But let me make this less wide so we can hopefully see all of it. Oh, it's a little thin, hang on. Okay, so on the left we have our TXY diagram at 1 bar, and on the right we have our XY diagram at 1 bar. Bubble curve, do curve, and as we can see there's our azeotrope right there. So we generated those graphs, but now we want to compare the plot with figures available online, so I'm going to go ahead and quickly look for that, and then I'll resume the video when I find something. So it looks like this is roughly about 1 bar, a little bit over, but here is from online a TXY diagram that I found. So ours is more compressed and theirs is more spread out, but as you can see visually they look very similar. And here is the XY diagram I found online. As I was saying, here's the azeotrope, and it looks pretty much just like our graph that we created. And since they look so similar, I would say that this is pretty reliable. Obviously it's not perfect, but just the fact that it matches graphs that we can find online from reputable websites means that we probably did a good job at least estimating what this graph should look like. I did want to touch base on azeotropes one more time. So it's a specific liquid mixture of 2 or more components that boils at a constant temperature, impossible to separate by distillation, which we may see that problem later on in this class, but it is whenever the two lines kind of touch. And as you can see here, the mole fraction in liquid, mole fraction in vapor, where it connects, that's the azeotrope. Continuing from part B into this part, we explained and implemented the code for calculating the bubble and dew pressures and temperatures, but for a system that is non-ideal, so we used the NRTL non-random to liquid activity coefficient model, and then we generated a few graphs of binary vapor-liquid equilibrium and compared those with plots that I found online. In the next part, we're going to go back to our Ratchford-Rice calculation and calculate the vapor-liquid equilibrium of this isopropanol water system and do some other diagrams with that. So thank you for watching, and part D should be out soon.